So now we're going to take a look and see how we can use that Ka values, which again are things that we can look up, right? You don't need to memorize Ka values. They're always going to be tabulated, or we can calculate them, or we can use them to determine other things like determining the pH. Let's say we think if we're given the Ka. And we're going to treat this, we're going to apply our equilibrium principles because, as we said before, these weak acids in aqueous solution are equilibrium systems, right? So this is an equilibrium problem applied now to acid-base chemistry. We're going to use the same principles that we learned back in the previous section. So we have calculate the pH of a 0.50 molar HF solution at 25 degrees. And again, the 25 degrees is just included just to specify that this equilibrium is happening at a particular temperature. We're not really going to look at changes in temperature and the effect on the equilibrium at this point, but we need to specify the temperature. All right, so we have our HF in H2O. This is going to act as an acid. This is going to lose our H plus. Where's the H plus going to go? It's going to go to the H2O to form H3O plus. Then HF, then after losing the H plus, becomes F minus. That is the conjugate base. And we can write the expression for this, the acid ionization constant, as H3O plus times F minus divided by HF. And we know at 25 degrees that the Ka value is 7.1 times 10 to the minus 4. This is something that we can look up in a table. Okay, so we can write the Ka expression, make it equal to the Ka value. How do we determine pH? Well, pH is equal to the negative log of the H3O plus concentration, right? So in order to determine the pH, guess what we need? We need the H3O plus. We need to solve for this thing. We know what we're going to get when we divide all these concentrations by each other. We should get the 7.1 times 10 to the negative 4. We still need to determine the other two things here, right? The F minus and the HF. And we're going to determine those using our equilibrium system. And specifically now, we're going to generate our ice tables with us. Okay, so we have our initial concentration. We're told we have a 0.5 molar solution of the HF. Initially, we have none of the products. As this reaction proceeds, we are going to gain a certain amount of products. We're going to produce, we're going to assign that as plus X. And it's plus X in both of these cases because of the stoichiometry is a 1-to-1. Similarly, on the reactant side, we're losing the same amount. So we're going to lose X minus X. So at equilibrium, then we can do the math and determine that equilibrium concentrations of the reactant would be 0.50 minus X, and then for the products would be X in each case. So what we can do is then substitute those values into our equation. So, okay, A expression. And again, I'll keep harping on this. This really boils down to this a math problem that we're doing. So we have our H3O plus, which we don't know. We're trying to solve for this right now. I'm sorry, we know that is being X. That's our H3O plus. So we have X times the F minus, which is also X, divided by 0.50 minus X, that's the HF concentration. And this, all of this together is equal to 7.1 times 10 to the minus 4. Right, I'm plugging in my equilibrium concentrations into that Ka expression. So what we do is we end up then with, if we simplify this, we have X squared on top over 0.50 minus X, and then this is equal to 7.1 times 10 to the minus 4. So we can make an approximation to simplify this. And the approximation that we're going to make here, or the simplification that we're going to say is that X is small. Okay, and X is small because this is inherently a weak acid equilibrium. So even though this is going to dissociate, it's going to ionize, we're not going to get an appreciable amount of the product. So if X is small, what we can do is we can ignore it in this part of the equation. We can't ignore it in the numerator because that's the only thing we have there. So we can ignore it in the denominator. So we can see that it's close to 0. So what I end up with then is I have now x squared over 0.50 minus 0. So this then becomes 0.50. X squared on top is equals 7.1. X 10 to the minus 4. I solve for x as a result. Okay, so I have x squared now being equal to 7.1 times 10 to the minus 4 times 0.50. So then x would be the square root of that entire thing, whatever that happens to be. I'm going to take the positive value, obviously. So x here becomes 1.9 times 10 to the negative 2. And what is x equal to? Well, x is a concentration of the H3O plus. So then what that means, to find my pH, I take the negative log of the H3O plus. I plug that in, negative log of 1.9 times 10 to the minus 2. And that is going to give me 1.72. That's my pH, right? And the pH makes sense. This is an acid, so the pH should be less than 7. And we're using a simplification here. What we're saying is because this is a weak acid system, we're assuming that this x here in the denominator is going to be so small that we can ignore it when we close to 0. So this just ends up being 0.50 in the denominator. It simplifies the calculation. And at the end, what we want to do is we want to check to make sure that the approximation is valid, right? So yes, we can use that to as a shortcut, but then you're going to check at the end. Is the approximation valid? And the approximation will be valid if x is less than 5% of the original acid concentration. Okay, so you always, if you make that approximation, that simplification, you want to check it at the end. So x here we found was 1.9 times 10 to the minus 2. The original acid concentration, HF here was 0.50. So all I'm going to do to see whether it's valid, I'm going to take that x value, 1.9, 10 to the minus 2, divided by the original concentration, and then I'm going to times it by 100. All right, so if I divide that, I end up with 3.8%. Okay, so that means then that my approximation is valid. X was so small, less than 5%, that it's a useful tool to use. I'm going to say check yes. So again, you know, with problems like these, it boils down to a math problem, and there are simplifications we can make, there are approximations we can make, so that the math ends up being a little bit more straightforward. Okay, so we talked about the ability for acids to ion and produce H plus, and the ability or the extent to which they ionize is a reflection of their strength. So recall that a strong acid ionizes completely, whereas a weak acid only ionizes partially. Why we're able to use an equilibrium system and equilibrium principles to study weak acids. And then the degree to which a weak acid ionizes is a measure of its strength. Okay, so the degree to which a weak acid ionizes is like that. So the way that we put some numbers behind that, the degree to which that weak acid ionizes, is by quantifying it in some with something known as a percent ionization. So the percent ionization is simply the if we consider a simple case of just having a weak acid like HA that we saw previously, the percent ionization is simply equal to the concentration of the hydronium or the concentration of the protons at equilibrium, that's what the EQ means, divided by the concentration of the original acid and its original concentration. And you can find that as subscript 0 after the concentration of the HA. This is a percent, so we're going to multiply this by 100. Okay, so obviously now the higher or the greater the percent ionization, the stronger the acid is. So greater percent ionization, that means we have more of the numerator, more of the H3O plus. That means it's a stronger acid. So what we can do again is something similar to what we did previously. If we have a 0.1, let's say molar concentration of what you have, this looks like benzoic acid. That's this thing. We have 0.1 molar solution to begin with. We can treat it again just like we did previously according to equilibrium. We have none of the products to begin with. Okay, during the course of the reaction, the stoichiometry dictates that we're going to gain a certain amount of the products. We're going to lose the same amount of the reactants. So at equilibrium, we have these have our equilibrium concentrations. So if we solve this, then for x, right, we end up with x there being equal to 0.0025 molar, right? And x is the concentration of it's here plus at equilibrium. We're going to take that, divide it by the original concentration, which was 0.100 molar. We're going to times that by the base. That's going to give us 2.5%, right? So that's very similar to what we did previously. Now we're saying this is a measure, this is a quantitative measure of the percent ionization of that weak acid. Now, what would happen if we were to, instead of starting with a 0.1 molar solution of the same acid that we had up here, what if we were to change the concentration from 0.1 to 0.05? So we're going from 0.1 down to 0.05. It's the same system, same equilibrium system with benzoic acid. Now the concentration is right, so here, right? And we're going to do the same thing, apply the same equilibrium principles. So numbers of products to begin with. The change that's happening here is gaining X from the product, we're losing X from the reactants. At equilibrium, we have our equilibrium concentrations. We're going to do the same thing. We're going to solve for X. And you find out here that X is going to be equal to 0.0018 molar. If we were to determine now the percent ionization of this specific example, where the concentration is lowered, we have 0.0018 divided by, now our original concentration here was 0.050 times 100, and we end up with 3.6% ionization. So even though we have the same, in both of these examples, we have the same acid, the same release acid, benzoic acid in both of these cases, the difference here is the quantum place of the original concentration. We have a 0.1 molar versus a 0.05 molar. And what that leads to is a difference in the percent ionization. So the smaller concentration has actually a higher percent ionization compared to the higher concentration that has a lower percent ionization. And this goes all the way back to calculating the reaction quotient and comparing it to Ka. Now, you're not going to go through that process right now, but you could do that in both of these examples, and you can see why the percent ionization increases, why the second example actually, that equilibrium lies to the right compared to the one above, because in the second one, the second example with the lower initial concentration, what we find is that our reaction quotient is smaller than our acid ionization constant, which means that that reaction has to go to the right in order to establish equilibrium. So the general principle there that we can extract from this example is that when if all other things being the same, if the concentration of the acid decreases, say concentration of the weak acid decreases, as we did in this example, the percent ionization increases. Okay, and that when you hear that on on initial inspection, it may seem counterintuitive, but if you actually plug the numbers in and you apply the equilibrium principles, it actually makes perfect sense based on the comparison of the reaction quotient Q to the acid ionization constant Ka. That relationship we can plot as a graph. Graphs are really good ways to show relationships between different variables. So here on the y-axis, we have the percent ionization increasing from 0 to 100. And then on the x-axis, we have the concentration of acid. And up here, you see this dashed line. The dashed line here is what would happen if we had a strong acid. But as we know, strong acids dissociate completely. They ionize completely, which is why that is a horizontal line at 100%. Now, if you compare that to a weak acid, which is the red line, right? If we start on the right and we work our way from right to left, so we're going opposite ways, the normal way you read it, right? So we have a high concentration here of the weak acid, high concentration, high concentration. You can see that the line is also flat, right? So for example, the percent ionization for a large or a high concentration of a weak acid, the percent ionization is small. However, as we lower the concentration, as we decrease the original concentration of the weak acid even more, what we find is that the percent ionization tends to increase, right? So there's an increase in percent ionization of the concentration of the weak acid decreases. Okay, we can see that graphically here. We would collect a bunch of data, do the calculation, plot them on a graph, or you can actually see that in the examples that we did previously.